So we're going to share the lecture screen. All right, close this. And get my participant windows back. That's not on the Zoom. Okay. Yeah, just, you may have to flag me down if you have questions. Let me see, where did my chat window go? I lost it again. Okay. Can you guys see the PowerPoint?
Yes, we can.
Yes, okay, great. We got that. Okay, so we're good to go then. So we started on this like 3 weeks ago. I barely remember talking about it. I'm assuming you guys don't remember hearing about it in any level of detail. Okay, there's my chat window. Thank you. I lost it. It somehow disappears. There we go. Got it back. Okay. So let's just start at the beginning of this, shall we? So the goal of the rest of the semester then is to take everything that we've learned in terms of how to model any kind of outcome and translate it into modeling any kind of outcome multivariately. So that requires introducing some new vocabulary and concepts as to how multivariate models are structured, when they're needed, etc. And so we will start there. So here we go, slide 2 of lecture 4. So you're familiar with this part already, right? The 3 parts of any generalized linear model, of which general linear models for normal residuals are a special case. You have the link function. So whatever transformation is needed of the conditional mean that's being predicted to make sure that the predicted outcomes in their original metric stay within bounds. So for instance, if we have binary data, the conditional mean of a binary outcome is the proportion of ones. I can hear Huey screaming in the background. This is going to be fun. To keep the proportion of ones bounded between 0 and 1, we use a logit link function or one of its friends, the probit, log, etc. Once we have that in place, then we can enter the model predictors in the same way as if it were a normal outcome. So we talk about intercepts and slopes. We can have simple effects and interaction terms and all that good stuff. You will hear me slip into this terminology. The model for the means is what I refer to in terms of the fixed effects, meaning how does a conditional mean get predicted for each person? Like the customization of the prediction via the slopes of the predictors. I call that the model for the means. And then the last part, C, the actual data, meaning the conditional distribution. So what do the residuals look like? Are they normal? Are they not normal? And so that's the question of whether, if it's not normal, what kind of distribution would be a better approximation. So Bernoulli, multinomial, the Poisson family, et cetera, and the translation from univariate to multivariate is going to occur in the conditional distribution or the linear predictor or both. We have to somehow adapt the model to capture residual correlation, so outcomes that are related between as a function of sampling. So in the case of cluster data, students nested in groups, something like that, or longitudinal data, outcomes nested in persons, outcomes from the same sampling unit are going to be more related. We have to build that into the model somehow. And it's going to be built either into the conditional distribution directly or indirectly through the linear predictor. So what's going to happen? So dependency, that word just means correlation. It means that the outcomes from the same sampling unit are going to be correlated. So this happens very commonly in otherwise cross-sectional samples of individuals when you have a repeated measures design. So you have the same person provide you with outcomes under multiple conditions. So for instance, under a condition of no feedback versus positive feedback versus negative feedback, something like that. Over time, longitudinal data are a classic case. This also happens when you have levels of sampling that are groups, such as families or dyads. So dyadic data, for instance, when you have a person and a partner of some type of relationship and you collect outcomes and predictors from both of them, multiple people from the same group and that kind of thing. Balanced versus unbalanced is an important distinction in trying to figure out how to model such data. Balanced is when the repeated measures are the same across all individuals. So if there's the same 3 possible conditions or the same 3 possible occasions. Unbalanced is the opposite, when the number of repeated measurements is going to vary across sampling units. So it happens in cluster data most commonly, where each group has a different number of persons potentially. So there's not a common set of persons because persons aren't specific entities the way that conditions or occasions are. It also happens in longitudinal data when people don't cooperate. So like they were supposed to come in, you know, at the first occasion, and then they were supposed to come back, say 6 weeks later, and they were supposed to come back, you know, 6 weeks after that. But in reality, some people came in 5 weeks later, some people came in 7 weeks later. It's kind of messy. And so I would refer to that as unbalanced in the sense that each person may have their own potential set of occasions, in the same way that each group might have their own potential set of persons. So unbalanced is not what we're doing this semester. Unbalanced is my other classes. If you haven't taken them, I'd recommend it because, you know, I'm awesome, right? And you're all on mute, so you're not going to argue with me, are you? No, radio silence. This is so damn weird. Okay. I think I'm going to have to like somehow see your pictures because otherwise I'm just muttering to myself at my computer like normal. Multi-level is the bomb.com. Correct, Molly. That is very correct. And it's also my bread and butter and why I have a job. It's because multi-level modeling is not easy. Anywho, we're doing multivariate models for balanced observations. So the same set of repeated occasions or conditions, the same type of people in a dyad. So you might have like the mom and the dad, or the partner and the person who's targeted, or something like that. So it's everything shares a common framework. We're doing models for balanced in this class. Okay, a lot of words on here. What do I want to say about that? Oh, okay, how are we going to estimate this? I've been using the 2 weeks that we haven't been in class to try and get ahead in terms of building handouts, so I've become much more acquainted with this in the last few days. There are 2 different types of software packages that you can use to estimate multivariate models. One is what you're already used to, what I refer to as univariate software. And so that is anything in SAS and anything in Stata where you have one column, and that one column is supposed to be your outcome column. So everything we've done this semester has been in univariate software. The only thing that switches is what link function we picked, what distribution we picked. You can trick that kind of software into doing generalized linear models that are multivariate as well. This is going to be most applicable whenever your model simply has to allow correlations between the outcomes from the same sampling unit and not otherwise think of them as predictors. They're all just outcomes. So for instance, if you have what would traditionally be a repeated measures ANOVA, say you have the same person has outcomes in 4 different conditions, and what you care about are mean differences across the conditions, but you just have to allow the outcomes from the same person to be correlated. Cool. If you want to examine differences in the effect of predictors, you can do it this way as well. So if you have, say, 3 different measures of depression and you want to know if your treatment is effective in reducing depression, you might want to see if your treatment has a different impact depending on how you measure depression. So that would be a case for a multivariate model where the 3 depression outcomes just need to be related if they're from the same person, and otherwise it's fine. We'll be able to build in those correlations pretty straightforwardly in that case. And so the first set of examples that I have to give you are of those kind. We're going to do a repeated measures ANOVA type analysis, and we're going to do a triadic data analysis of answers from a mom, a dad, and their adult child, where we have predictors from each and answers from each. So we're going to do those as the next couple examples. Where it gets tricky then is the second part here, multivariate models that must be instead estimated using truly multivariate software. I make that distinction, meaning we're not just tricking univariate, but the software has to allow multiple columns of outcomes, because in these models, a given variable may need to be both a predictor with respect to certain outcomes and an outcome with respect to other variables. So the classic example of this, can you all see it when I highlight this thing here? I think it shows up, right? The X to M to Y. Yes, yes, you can see it. Okay. Yes, thank you. I got the chat window open. So we're good on that. So in the classic example of mediation, the logic here is that you have a predictor X, such as some sort of manipulated variable that then causes differences in a mediating variable, and changes in that mediating variable then cause differences in an outcome, something like that. So M here is tricky because M is an outcome with respect to X, but M is also a predictor with respect to Y. And when you have that situation, you cannot trick univariate software like GLM or Mixed or any of that into doing these models and get all the effects that you want. Any tricks are going to have to leave some of them out, which is no good. So the type of software that we'll need to pick up for this is what's known more commonly as structural equation modeling software. It's called path analysis if the model involves only observed variables, which is everything we've done so far. If it incorporates latent variables instead of just observed variables, it's called a structural equation model. If you're interested in the structural equation models, I'm teaching that class in the fall, possibly online, possibly from my office from the beach here, who knows, but we'll see. We're going to focus on just observed variables, so path models is the type of software that we have to pick up. Stata does it. Stata has a routine that's called SEM or SEM. If you're from Europe, they call it SEM modeling. And GSEM, which is generalized SEM modeling. That's redundant. It's structural equation model, so you can't have a model modeling. But anywho, so Stata can be used for a lot of this. I've started poking around into some of its limitations, and it does seem to have some. So when we get into that unit, I'll have more to say about that. But Stata can be used for that. SAS has a package called KLIS that does theoretically do path models, but it has a lot more limitations. It doesn't allow any kind of non-normal outcomes, and it insists everything has to be normal, including the predictors. So I'm not even going to try that. Okay, something slamming behind me, don't know what that is. I'm not even going to try that. Instead, I'm moving to M+. So one of the things that hopefully happened over break is that each of you inside the virtual desktop should have access to M+ software. At some point this week, I would like you to try and log in and see if you have it. The restrictions on M+ are much stronger than on other pieces of software. I think the university only allows like 8 people to use it at the same time or some shit like that. So I'll have to think about that in terms of what kind of our last assignment is going to be. But we're not going to be able to use SAS for truly multivariate models. We may be able to use Stata, but maybe not for everything. So I want to have you pick up another package, M+, so that you have the capacity to do any kind of multivariate model that you can think of. M+, by the way, is also what I'm planning on using in the structural equation modeling class in the fall, possibly Stata to some extent. Again, I'll have to see exactly what it's capable of because I haven't learned as much about that as I have M+. So point being, to start with, we're staying in Stata and SAS, using the same packages you already know, but tricking it and using those packages to do multivariate analysis. Later in the spring here, we're going to be transitioning into path analysis software instead. What is common across all of these is the continued use of likelihood estimation. So we are trying to find the parameter values that make the data most likely for the entire sample, and then using that sum of the individual log likelihoods to compare models that have more things in them or fewer things in them. So nothing that we're doing is going to be in the context of least squares. What that means is that not everybody has to have every outcome to be included. You can have some people only have some outcomes and still keep whatever data they do have. What happens to missing predictors, though, is more complicated, and we'll talk about that later, because you can have missing predictors to some extent, but not without certain assumptions. So, all right, this is so weird, just muttering to my screen here without seeing any of you. How are we doing so far? Can I get an emoji or a thumbs up or a hello? Thank you, Terry. She sent me happy sign, going well. Okay, so you're all still there? Yeah. By the way, in digging through the Zoom options, yes, thank you, everybody. Oh, that makes me feel better. In digging through the Zoom advanced options, I came across like a spyware version where if any of you change your focus to not have me like in focus on your thing, it will like beat me and let me know that you're not listening anymore. I did not invoke that setting because I thought that was like too much Big Brother, but just so you know, it's possible that your instructors might be doing that. OMG, exactly. So no, I did not do that, but it has the capacity to know when it's in focus, when it's not. I've already been in the Zoom meetings I've had not in focus for good chunks of the time, and so I didn't want that. Yeah, learned that on Twitter the other day. Yeah, Zoom is kind of creepy, but it's what we got. So, all right, back to the story here. Where are we at? Back to general linear models. I love how I'm looking at my slides as if I've never seen them before. Like, no, really, I wrote these not that long ago. It's just like my mind has been shot since it's like I'm mommy all the time now. All right, so how are we going to put relations in the model between the outcomes from the same unit? So I'm going to say people to start with, but it's also like the same family, the same group to the extent that the observations are balanced. Like you might have one boss and one employee. Like that would be an example of balanced. For a family, you might have the mom and the dad, or the grown-ups versus the kids, something that's balanced like that. You can do it directly, which is super easy, or you can do it indirectly, which is a little more complicated and harder to know that it works. So directly is just, we put instructions into the model that says residuals from the same unit get to be correlated at the end. That's it. In order to understand how this works, we have to transition from describing models using scalar notation, so like this here, into matrix notation. So I prefer scalar notation when at all possible because it's a lot more transparent. What's in a model in terms of which predictors and which outcome is readily visible, and it's a lot easier to understand as a result. But just looking at this equation doesn't tell me anything about the e's, right? It doesn't say whether the e's are all supposed to be independent, or some of them can be dependent, or some of them have different variants, or whatever. Like it's not complete enough. And so one way to make it more complete is to switch to matrix notation. So let's say that I have one outcome and I'm describing it for 6 people. So I have this model right here in scalar notation can be written like this in matrix notation, where y is a vector that holds all the outcomes across people. X is a matrix, so it's more than one row or more than one column. Vector is only a row or a column, from what I understand. And please correct me, math people, if I get any of this wrong. X is a matrix that holds the predictors that have fixed effects. Slopes that are the same for everybody. Beta is a matrix that holds the fixed effect estimates themselves, so the intercept estimate, the slope estimates. E is a matrix that holds everybody's residuals. And when you write it this way to describe the predicted outcome, you can also describe the predicted variance of the outcomes. And that works out to be this type of what's known as a diagonal matrix here, where there's zeros in all the off diagonals, and on the diagonal is the same residual variance. What this is saying is that everybody shares one residual variance estimate, and there is no covariance or correlation between the residuals across people. So even though each person is a row here or a column, and so one person can't have a residual variance all by themselves, we borrow across people to estimate one residual variance. And so it's the variance of the e's, and that one number is assumed to describe everybody to the same extent. That's the general linear model. We're saying that the e's are independent. That's what the zeros mean here. That they are normal. That's not visible on the slide, but that's the E distribution right here. I guess it is visible, but not the matrix is what I was trying to say. And everybody shares the same residual variance. So how does this have to change if we want to have multivariate data instead, more than one outcome per person? Well, let's look at how it works for univariate, and then we switch to multivariate. So when we say we're using a general linear model, what we're saying is that we are picking the univariate normal probability density function by which to calculate our likelihood. And so that's the formula right here. If you know what each person's predicted outcome is supposed to be and you know the residual variance, you get a number. And you take that number, take the log of it, sum it across persons, and that quantity is your log likelihood. So that tells you the height of everyone's combined data. And the way that the model figures out what the parameter value should be is it's the ones that make the height the tallest. So they'll try out values of the slopes that in turn create the predicted outcomes. It'll try out values of the residual variances, and it tries them out until the sum of all of these individual log likelihoods doesn't change very much. When you're dealing with normal, all you have to know is the residual variance and the predictor slope values fall out. There's actually an equation for it. They don't have to be found. If you're dealing with another type of probability density function besides normal, the slopes also have to get found as part of the searching process. But point being, each person has one number that summarizes their height, and we sum across persons assuming they're independent of those log likelihoods. Easy peasy. So here's a visual. I think I've showed you guys this before. The idea that the answers that are right, in this case from an empty model, the green line is the ones that across everybody make everyone's sum of their data, their heights, the tallest. So like the red line is not the right mean or the right variance. It gets taller for some people, but not everybody. And so it tries to figure out what values make the combined function the tallest. This same idea applies in models that have predictors, not just empty models, and we assume that there's still only one residual variance that's needed, and that means that the model works equally well along all of the values of the predictors. Well, if we have more than one outcome per person, then we have to change the model to account for that, but we're going to cheat in order to use the same software and pretend like we still have one outcome. So in order to use SAS and Stata, GLM, or mixed, or any of the things, limits, the things that we've been using so far, we have to take what is multiple outcomes, which would normally be stored in separate columns, and convert the data structure into one in which all of the outcomes are in a single column. And so the type of data that multivariate data are typically stored is this type of wide structure here. It's where it's one row per person, and separate outcomes for the same person show up in separate columns. We have to take a data structure that looks like this and instead make it look like this. And this process is known colloquially, as stacking. It's also known as reshaping. That's the command in Stata by which to do this. I'll show you how to do it in both of the programs in the example. And this is what's known as long format. More generally, a row is the lowest level of sampling. And so if multiple people have multiple outcomes, each row is one outcome for one person. So person one here had two outcomes, one at, for example, time 1 and one at time 2. In the long structure, they have 2 rows. Person 2 has 2 outcomes, they get 2 rows. And so it's like a per person transpose is what happens. So Y then is the new outcome that goes into the model. And if you just put Y in, the software doesn't understand that Y is made up of 2 different outcomes. That's where you also have to add a column that indicates which outcome is which. And so if I have time 1 and time 2, I may center it such that the first occasion is this time 0, and so my predictor X would be 0 and 1. Ding dong. Someone's internet kicked her off. Welcome back. Okay. So we have functionally what looks like one outcome, univariate data, and we have an index that tells us which is which, and that's going to be important in trying to figure out how we would predict time 1 outcomes differently than how we would predict time 2 outcomes, because it's still possible to do that, even though they're stuck in the same column, because we have an index as to which is which. So if we have data that are from 3 persons and 2 occasions, like on the previous slide here, now we change the notation such that rather than talking about a matrix that holds all the observations across everybody, each person gets their own set of matrices. So Y sub I is the vector of outcomes for person I specifically. X sub I is the matrix of predictors that have fixed effects where it's person I's predictors specifically. Beta is still the fixed effects. It doesn't get an I because everybody shares those. By definition, fixed effects are shared, they're constants. And E is the matrix of residuals for person I. And so if you write it out, for instance, time 1 and time 2, it would look like this. And now what we have to do is figure out what we're going to do with the E's from the same person. So here's a new vocabulary word. Welcome to something called the R matrix. This is terminology that's commonly used in manuals of software. That's where it's coming from, is mixed in particular. It talks about the R matrix, the G matrix, and the B matrix. Analogous things are present in Stata for the residuals. But what we have to determine in these models is what to do with the E's of each type and whether or not to allow a covariance. So at most here, we could say that there is a variability of the E's from time 1. Stop that. Time 1. A variability of the E's at time 2. And this thing right here, that's a covariance between the E's at time 1 and the E's at time 2. And so if we were to take our 3 persons and come up with an overall matrix, sort of stacking all of the individual matrices together, we end up with this pattern here where the E's from the same person have a relationship between them. They have a covariance. And so these little pockets here, this is known as a block diagonal structure, where it's like, here's the stuff for person 1, here's the stuff for person 2, here's the stuff for person 3. People are independent, as seen by the zeros elsewhere. So we're just going to change the structure to say the E's from the same person get to have a covariance, and we have to decide whether or not the E's from different outcomes need different variance estimates to go with them, whether they should be the same or whether they should be different. And those are nested models for which we can do likelihood ratio tests. If we had 3 outcomes, let me see here. Oh, no, not yet. 3 outcomes is coming. Yeah. How do we do this? Rather than coming up with a height for each person that's based only on their one outcome, their height is based on all their outcomes, multivariate height. For instance, if I have 2 outcomes per person, then I can show height in 3 dimensions, where I have, say, one of the outcomes is X and one of them is Y. If there is no relationship between them, the analog of just a scatter plot that has like a big circle in bivariate space would look like this sort of circly hump thing in multivariate space. It looks like a taco if they have a positive covariance or a negative covariance where the direction of the taco conveys the direction of the association. But the same concept as univariate height applies, just in multivariate space. So this is a scary slide here, number 13. I'm trying to compare what it looks like for the univariate normal probability density function PDFs to switching from univariate to multivariate. And so everywhere in univariate where we had a residual variance that we have to know to get a person's height, now we have to know the R matrix. That means we need to know the residual variance of each outcome as well as their covariance, 1 or more depending on how many outcomes you have. And so that switches from variance of 1 outcome to variance of many and covariance. And the outcomes to be predicted, we've got more than one of those. And so the y sub I minus y hat transforms into this y sub I minus x beta, which gives us the predicted outcomes from the fixed effects and the predictors. So it's the exact same concept in terms of height. It's just that each person's height is a multivariate height. It's the height of their 2 outcomes together. And that takes into account that their outcomes get to be related. We assume that everyone's outcomes have the same covariance. So there's 1 covariance, for instance, between all the time 1s and time 2s. People don't have different pockets of covariance unless you want to specify that, but that's typically not the case. So this is pretty cool in that if somebody has a different number of outcomes, it's not a problem. So if I had somebody who had 1 occasion only, their height is univariate normal height based on their 1 occasion. If somebody has 2 occasions, their height is multivariate normal height based on 2 occasions because the R matrix would be 2 by 2. If somebody had 3 occasions, then their R matrix is 3 by 3 and they have multivariate height. So height can be calculated regardless of how many occasions that somebody has. The rule is, though, in terms of what happens to cases that have missing data, is that each row must be complete. What a row means is different than what it used to be. Like a row used to be a person before. Now a row is an outcome per person or per sampling unit. So if I have somebody who's supposed to have 2 outcomes, but they only have 1, none of the data from the missing outcome is included because that row is incomplete, it's gone. But I do get to keep the row from the outcome they do have. And in so doing, this likelihood process makes an assumption called missing at random. Question from the thing here. So the zeros would probably not be there if it were dyadic data.
Yeah, that was a question a while ago. It was in the matrix. It's okay, we don't have to talk about it. But you were saying how they're not related.
Yeah.
So if it was like families or dyadic data, you wouldn't assume the zeros, right?
Is it this slide that I'm on, slide 11?
Yes.
Okay. So like each block would be a separate family, each square.
Oh, okay.
So it's the families aren't related. That's where the zeros are.
Yeah.
But the people in a family are related via the covariance between the 1 and the 2.
Okay.
Yep. If families are related, then this model isn't enough. And that's where we get into multi-level land. So yeah, I apologize. Thanks for stopping me. I'm looking at like 3 windows at the same time here and trying to keep track and I get in the zone. But yeah, so what happens to missing observations then? We're assuming that anything that's missing is missing at random. That phrase does not mean what it sounds like. What missing at random means is conditionally random, meaning there is a reason why the observation is missing. Like if it's high, it's more likely to be missing or something like that. It's that we know what the reason is based on the information that we have about the person. Said differently, missing at random means the shape of the likelihood mountain here would be the same shape if I had more observations contributing to it than if I had fewer. Like the data that are missing would not change my picture of what this person's data looks like. They would just sort of fill in the holes. Missing at random is a very common complaint from reviewer 3 because missing at random is not testable. By definition, you are missing the data needed to test it. There is absolutely no way to know for sure that you have all of the reasons accounted for why something is missing. What you can test is a stricter assumption that's called missing completely at random, which is what you're forced to make if you are missing predictors. So if you have somebody who has 2 outcomes and you put a predictor into the model that is a person level predictor, something that is constant over time, then you have to throw out all of their data because each row would be incomplete. In that case, you are forced to assume missing completely at random, which is what it sounds like, that there is absolutely no reason why you didn't get their data. So all of the effects using that predictor are just fine, even though you couldn't include extra people. If the data that you would have had change the effect of the predictor, that's where you're in trouble. So missing completely at random is testable because if you find anything in your data set that predicts who has data and who doesn't, then by definition, it's not completely at random, it's predictable. So the use of likelihood estimation solves some problems with respect to missing data in that it allows you to maintain incomplete people because you get to keep the rows that are complete. But if anyone's missing predictors, they're gone. There are 2 solutions for that: multiple imputation and turning the predictor into an outcome, and both of them require distributional assumptions because you're functionally going to either complete them repeatedly with error or treated as an outcome. I will show you how to do at least one of those later in the semester. So for now, what we're going to do is subset our data so that, to start with, all of the rows are complete. So that requires anticipating which predictors are going to be in the model and kicking out cases ahead of time that don't have them. That way our sample stays constant across models, our definition of height stays constant, and -2 log likelihood and AIC and BIC and stuff like that remains comparable. So it's obviously not good to dump people because they're incomplete, but that's what we're stuck with when we use this sort of software without doing anything else, just tricking univariate software into being multivariate. So the slide that I thought was coming, which I apparently decided to put later, this is what it would look like if you have 2 people and 3 outcomes. Now your R matrix is 3 by 3, where within a person, the outcome from time 1 and time 2, time 1 and time 3, time 2 and time 3, they all get to be related to each other, but between different people, there's no relationship. So like if this was family data and 1 was mom and 2 was dad and 3 was kid, members of the same family have a covariance between their residuals, but there's no covariance across different families that's built into the model. Okay, how are we doing? You can talk now. I'll unmute you guys, or, you know, emojis, whatever. Good, we're still okay? Good, okay. Questions from the audience? Oh, that's a big happy face. Okay, happy D. I'll have to learn that. Okay. So the only thing that we have to worry about really is what this R matrix should look like. And for these kind of data, there's really only 3 choices that make sense. So in SAS, we're going to add a line that's either going to start with the word repeated or random into mixed or glimix. And in Stata, we're going to add an option that goes, it's called residuals, where in here, the question marks, this is a placeholder for the type of structure that you're going to ask it to do. So there are 3 structures. They differ in whether or not you are saying that the residual variance should be the same across outcomes or not. If you decide that it should be, then the next question would be whether or not the covariances between outcomes are the same or not. And if the residual variances are not the same, then might the correlations still be the same? So this is a bit abstract, but let me try to show you what the patterns are that you would be choosing from. So option 1 here is the answer key. This is what's known as an unstructured R matrix. Unstructured, that term means everything just gets to be what it wants. There's no constraints whatsoever. So if I had, say, 3 occasions from the same person, an unstructured covariance matrix of the residuals would say that the residuals from outcome 1 have a different variance than the residuals from outcome 2 has a different variance from the residuals of outcome 3. So 3 outcomes, 3 variances. It also makes no constraints on the covariances. So this one right here, covariance between outcome 1 and outcome 2 gets to be whatever it wants. Covariance between outcome 1 and outcome 3 and outcome 2 and outcome 3. And then the top half of it is just a reflection. It's the same information. So there's only 6 unique terms in here. There's 3 variances and 3 covariances. You will see in your output for these programs the R matrix that you can ask for it to be printed in this format. And you can also ask for it to be converted into a correlation matrix known as R core in SAS in particular, in which there's 1s on the diagonal for the variances, and the correlations are computed as the covariance divided by the standard deviation of each of the 2 variables multiplied together. So on the good side, this can't be wrong. So why not just let it be unstructured always? Well, if you only have 2 or 3 occasions, maybe 4, that's fine. If you have more than that, the number of parameters you have to estimate grows exponentially. So the formula for how many different elements are in this R matrix depends on how many outcomes you have, little n. It's number of outcomes times number of outcomes plus 1 divided by 2. So like if you had 10 outcomes, that would be 10 outcomes times 11, that's 110 divided by 2. That would be an R matrix that has 55 things to be estimated, and that's before you even start talking about predictors. At a minimum, you better have 55 people to pull this off, but that's really not good. So unstructured works well for balanced outcomes, which is what we're talking about. So each person can share the same structure of an R matrix, and there's not that many occasions. This idea of unstructured, let everything be what it wants, this is otherwise known as MANOVA. It's known as the multivariate analysis of variance, or when you're talking about repeated measures analyses, it's known as the multivariate approach to repeated measures. So you will see people use those words to convey the same idea in terms of what you're saying about the residuals. Each outcome gets its own variance. Each pair of outcomes gets its own covariance. The difference is that when people use those words, MANOVA or repeated measures, they're talking about least squares estimation most of the time, not likelihood. So there's a difference between model and estimator. In longitudinal analysis, for instance, people sometimes say, oh, ANOVA is terrible for longitudinal data. No, ANOVA is just fine. ANOVA refers to one of these sorts of patterns. For instance, multivariate ANOVA is this pattern right here. What's wrong is when you use least squares. When you use least squares, you don't get to keep incomplete observations. Whole people are listwise deleted. That's the problem. So the model is fine. It's the estimation method that causes problems with missing data. So unstructured R matrix is the same thing as MANOVA in theory, but using likelihoods so that we get to keep incomplete cases, and so that we have a lot more control over what the model, in terms of which predictors predict which outcome can be. It's completely custom if you do it in this mixed framework, and it's not custom at all if you do it in the MANOVA framework. So have you guys had MANOVA in your classes before? Anyone? I'll take the lack of response as a no. Okay, good, so I don't have to reteach you. In interest stat, but it's a bit hazy. You just forget about it, Hansi. Just forget about it. You never learned it. Just let it go. It works out that the lambda thing that you're supposed to report from MANOVA is a transformation of a likelihood ratio test. So it really is all the same. It's just that this approach is a lot more flexible than what you would learn when you're stuck with these squares. So no worries. Okay, so this is one choice for what your R matrix should look like. Everything gets to be what it wants. It's going to fit the best. Here are two others that are reasonable for this type of data. Option 2 on the top here is something known as compound symmetry heterogeneous. More briefly, it is different variances for each outcome, but a common correlation across outcomes. So the way the covariance matrix is built is on the diagonal, each type of outcome gets its own residual variance, and the residual covariance shares a common correlation that's known as the CHS thing, CSH, excuse me, times the standard deviation of the two variables. And so if you do the correlation version of the matrix, it looks like this. So even though there's different residual variances across outcomes, it doesn't matter which outcome is which, all of the residuals are equally correlated. This one is not available in Stata. I looked high and low, even tried to trick it, and I was unable to do so. So that one's not available in Stata. The only other one that would be reasonable to consider for this type of data is compound symmetry, which implies homogeneous variances, and that's this thing right here. This is the idea that all of the outcomes share the same residual variance. It forces the residual variance to be equal across outcomes, and it forces the covariance across outcomes to be equal too. This model is known as the univariate approach to repeated measures ANOVA if you're using least squares. It is also known as a random intercept only model in the world of multi-level modeling. And we will see this idea come back for generalized models in which the residuals are not normal. So for right now, we're focusing just on regular normal residual models, no pun intended, normal residuals. Then we'll hit the translation to generalized. So there's just three choices that you would have to consider in terms of what your R matrix look like. Unstructured is the most complicated, but it fits the best. Then the question would be, can you get away with something simpler so that you can save the number of estimated parameters? If so, then that in theory should give you more power. Okay, how to pick likelihood ratio tests. You already know how to do this. It is the difference in -2 log likelihood across your nested models. And in this case, you are allowed to treat it as a regular chi-square, not a mixture. So of the possible R matrix patterns, the one that has complete independence, that was the first one that we looked at here on slide 6. This structure that's diagonal is known as VC. It means equal variances, no covariances whatsoever. That's the simplest possible model you can have. If you add any kind of covariance to that, let me find, here we are. If you add a covariance, then that becomes compound symmetry. If compound symmetry fits better than VC, then you know you have significant covariance, you have some kind of dependency. Then from there, okay, if I have some dependency, is it constant dependency or does it vary by outcome? And so if you want to say I have constant dependency, but each outcome needs a different residual variance, that's CS nested in CSH. And then the last one is unstructured, where everything gets to be what it wants. So in terms of order, VC, which is diagonal, is the simplest. Then comes CS, which allows a covariance but forces the variances to be the same. Then comes CSH, which allows the variances to be different but still forces the correlation to be the same. And then comes unstructured, which allows everything to be different. So you can always compare these relative patterns and see if you can find something simpler than unstructured that still fits as well. So this is an example of hypothesis test where what your goal is not worse, because you know that unstructured is best, always best by -2 log likelihood because it is the data. The question is, can you get away with something that's simpler, that has fewer parameters and fits as well? If so, you should do that because then you, in theory, should have more power. So I'll show you how to do that in our example. So just sort of more generally, I wanted to sort of revisit this idea of when you can do likelihood ratio tests and when you can't in terms of model comparisons. And so almost always in statistics, model comparisons are between nested models where one is a subset of the other. The question is, how are they nested? So if the models to be compared differ in their model for the means. So what fixed effects are included? So for instance, if you start with an empty model and you add predictor A and predictor B, you don't have to do a likelihood ratio test to find out whether predictor A and predictor B significantly contribute to the model. You get a p-value for each of those that tells you that directly, and you can ask for a multivariate wald test to test their joint combination. If you do so with degrees of freedom in the denominator, that's an F. If you do so without degrees of freedom in the denominator, that's a chi-square, which is what happens in GLM software, in Stata, for instance. But you don't have to do likelihood ratio tests to make decisions about fixed effects. You can always do these F or chi-square tests to test their joint combination. If you wanted to do likelihood ratio tests to test models that differ in fixed effects, then it's only valid to do that if you're in regular flavor maximum likelihood. For models with normal residuals, you should instead try to be in residual maximum likelihood, which offers better estimates of the variance components. And so this is REML rather than ML. The reason that we had not done likelihood ratio tests for fixed effects at any point in the semester is because I didn't want to have you guys to have to memorize this rule. It makes it harder than it needs to be. You can always do multivariate wald tests. That's the test statement in Stata, the contrast statement in SAS to test the joint combinations of fixed effects. You don't have to do likelihood ratio tests. When you do need to do likelihood ratio tests is in deciding what the model for the variance should be. So which R matrix pattern fits relatively best, for instance. You cannot use the p-values that show up next to the variance component estimates because they're not valid because variances are not unbounded. They're bounded at 0. You can use likelihood ratio tests to make decisions about the variance model if they're nested. And so we saw this earlier in the semester and in your last homework, comparing Poisson and negative binomial. They differ in one parameter that allows the variance to exceed the mean in a quadratic fashion, that stretchy K thingy. Likewise, binomial and beta binomial are related because beta binomial has an extra stretchy thing that again allows the variance to exceed the mean in a different pattern. So anytime that you can phrase one model as nested within the other, and you're asking a question about variance or covariance, that's a likelihood ratio test. The fixed effect should be kept exactly the same between models so that you get the best test possible. You don't want to confound things. So anytime you're making decisions about variance regarding nested models, that's a likelihood ratio test. Anytime you're making decisions about fixed effects in terms of nested models, that's an F or a chi-square multivariate model test. So there were some questions about that I know earlier in the semester, so I wanted to kind of hit that point back again. So, okay, I'm going to pause, take a sip of Diet Mountain Dew, of course, can't teach without that, and ask for questions. Okay, chat window is not moving. I don't see any little icons next to your things. Thumbs up. Okay, all right. Okay, let's see, what do I want to do? I'll talk a little bit more about this and then we'll jump into the example next time. That's what I want to do. So why would you use multivariate models? What are the kinds of questions that lend themselves to this approach? So there's two ways to think about multivariate modeling as a strategy. One is I have to because my outcomes are related to each other. In order to predict them all at the same time, you have to be able to build in those relationships. That makes sense. But there's a lot of situations in which people collect different outcomes and they still predict them in separate models. Like I have a measure of anxiety and I have a measure of depression and I have a measure of this and I have a measure of that. And so I'm going to run 5 different sets of models to predict them all. That's all well and good, but that's not necessarily the best strategy. Whenever you're predicting outcomes singly like that, you can only answer questions about how predictors relate to each outcome. You can't answer questions like, is this predictor stronger for outcome A than outcome B? If your outcomes are on the same scale, such as if you have a repeated measures design, where you have, say, response time in the example I'm going to show you in one condition versus another. Well, a natural question would be, are they faster in one condition or slower in one condition? In order to answer questions about mean differences across the repeated measures, across the per person outcomes, you have to have them both in the same model. To answer questions about differences in the size of predictor effects across outcomes, they have to be in the same model. If you have the same effect of a predictor across multiple outcomes, like that's not different, you can actually constrain it so that the predictor effect is shared across outcomes, and then you have potentially greater power in testing that effect. The only catch in thinking about this is whether or not things are on a common scale. So for instance, in dyadic or family data, I have another example I'm going to show you where 3 different members of the same family each completed the same instrument. The outcome is attitudes about gender roles in marriage, where higher scores mean the person has more conservative, traditional attitudes about gender roles. I have a gender role opinion from an adult child, a gender role opinion from a mom, and one from a dad. They're on the same scale theoretically, right? Like it's the same scaling, it's the same instrument. And so you might be tempted to say that dads on the whole are more conservative than moms, right? Because you can test mean differences. And you could say that, for instance, education of the participant has a bigger effect in differentiating the fathers than it does in differentiating the mothers. You can say those sorts of things. In such situations, it can be convenient to leave them in that original metric because the scales themselves have ready meaning. But if it's something to where they're not on the same scale or it's questionable, it would be probably more advantageous to z-score them or otherwise transform them to the same metric. That way you're not comparing apples to oranges. So it's kind of a gray area as to whether that's necessary, but it's certainly necessary if you have outcomes that are on completely different scales. And what you really want to know is sort of like effect size, not just in a 1 unit change in y per x sort of language, but in like a strength. And in that case, what you're interested in is more like standardized regression coefficients. You would want to standardize your outcomes to the same scale so that the predictors have a better chance of being standardized. And if you want to compare across predictors, you would standardize those as well. So point being, there's more types of research questions that can be answered in multivariate models by putting multiple outcomes into the same model and predicting them separately. Here's an aside, by the way, if you're interested in predicting difference scores, multivariate models are a much better strategy than controlling for one of the outcomes and predicting the other. So this is a thing that needs to die. Like if you have pre-test, post-test, you can estimate a multivariate model that predicts pre-test scores simultaneously as one outcome and predict post-test scores as another outcome simultaneously. And you can ask the model to give you the difference as a parameter so that you can predict each set of scores as well as change between them. That's a multivariate model. I'm going to show you how to do that. An alternative that people do instead is to use pre-test scores as a covariate in predicting post-test scores. That is known as a residualized changed model. It's stupid. Don't do that. It assumes that if you're looking at any other predictor that they were equivalent on pre-test in order to generalize to post-test, which is almost never the case, except in a fully controlled experimental setting. So I would encourage you to do multivariate models instead of controlling for one occasion and predicting the other variants. So there's my soapbox. So differences in effect size. Just to remind you that the line in the sand for significance of an effect is not a direct way to answer whether an effect is different between outcomes. So if I ran a model, for instance here, predicting DVA, and I have a predictor and the effect size for the predictor crosses this arbitrary line in the sand where I declare significance. So I would say, yes, my predictor significantly predicts DVA, hooray, DV meaning dependent variable. And I may have another DV and a same predictor, and it's significant too. Well, the fact that they're both significant does not tell me if those effects are of the same magnitude. In order to answer that question, I have to ask for the difference in the coefficients directly and get a standard error for that difference in coefficient, and that can be tested against 0. So I can't say that the pattern of findings is the same with respect to my predictor across outcomes. Yeah, they're both significant, but that doesn't mean that they're of the same magnitude. Likewise, what if I found a predictor had a non-significant effect for one outcome, DVA, but a significant effect for the other outcome, DVB? Does that mean that those predictor slopes are different? Not necessarily. Just because one crossed the threshold for significance and the other didn't, doesn't mean that they are differentiable, distinguishable. Again, the test of whether those slopes are actually different has to be done within a model where you can get a standard error for the difference. So anytime you're tempted to say that this predictor matters more for one outcome versus another, the best way to answer that question is to put all the outcomes in the same model and to do the test for them. How to put them all in the same model is the tricky part. The first example I'm going to show you is a more traditional approach that looks more like what you're used to. The other options are more, lend themselves much better to multivariate data where each outcome stands sort of on its own. And so that's what we'll talk about later on, this second part here. The first example that I want to show you next time, since we're running out of time, is going to be a repeated measures design where we have 4 conditions per person. And so in that case, we'll have a single model intercept. We'll have differences across the conditions as one set of fixed effects, and then moderators of those differences as another set of fixed effects. And the only thing that's really different in terms of what you already know how to do is the preliminary step of trying to decide what kind of R matrix that we need, whether or not each condition outcome needs to have its own residual variance, whether the same covariance can stand across all the outcomes, or whether those should be different. That's the multivariate aspect. From there, everything is pretty much the same. So, all right, I think that's a good stopping point. How are we doing, folks? Does anybody want to ask me to revisit any of this or clarifications? Doing okay, good. Well, that's one person. Good, okay. Does anyone want to talk about, does this give them ideas for analyses they could do? No. Okay. Well, fair enough. So my plan then for next time is to pick up with example 4A. We will look at how to fit these sorts of multivariate models in SAS and in Stata. You have a formative assessment that is available that will be due on Monday. You can start looking at that if you want. You might be able to answer some of the questions, and then you'll be able to answer all of them by the end of Thursday. I went ahead and put those up early in case anyone wants to try. They're really bored and they want to get working on things. I also this morning put up your next homework. We haven't gone over enough code for you to be able to do most of that yet, but I just wanted to get it up in case people had extra time again to work on that. The recommended due date for that is not until the 21st, so that's a few weeks out, but being ahead is better than being behind. Hopefully by the time we come back, I will have figured out how to do the regular OBS software on this computer, or have reset my laptop, which will be painful, but possible maybe, so we'll see. All right, I'm stopping the share. I'm opening up my window.